So yeah, we finished up chapter 13. Hopefully the stoichiometry part of 13 made sense.
Mr. White,
Yes.
the stoichiometry part of 13 didn't make sense.
What part of it didn't make sense?
Well, the stoichiometry part.
Stoichiometry part?
Mm-hmm.
So the gas laws you're okay with?
Yes, I'm okay with those. Those make sense. But, like, not the other, the stoichiometry.
Okay. Well, remember, it's all about balanced equations and ratios. That's what stoichiometry is about. Okay. If you have gas to gas, you can use those coefficients. You can use those coefficients to just say liters to liters. Okay, remember, because of Avogadro's principle. But yeah, so.
Can we, like, go over it some more after you've been teaching the lesson today?
Yeah, after we get through today, we can look at that again. Okay. Today we're moving into chapter 14. Chapter 14. And that's titled Mixtures and Solutions. Okay. Mixtures and Solutions. So now we're mixing things together to create something. Okay. Not doing a chemical reaction quite yet right now. Just kind of mixing things to figure out. We're going to talk about different ways that you can mix things. Okay. Now, a mixture we've talked about. Okay. A mixture is, well, just like the name would make you think, we are mixing two things together. We have a mixture, and yeah, we can have two different types of mixtures. We can have heterogeneous mixtures and homogeneous mixtures. You will also hear people say homogeneous mixtures. I've heard both. I don't know that either one is more correct than the other. I don't know that I've heard many people say heterogeneous, but you might hear somebody say that. Anyway, what I have heard most from my chemistry teachers, heterogeneous and homogeneous. Okay. Now, the heterogeneous mixtures mean that we can see the different parts. Okay? And we've talked about this already a little bit. This should sound at least somewhat familiar. Remember we said that heterogeneous mixtures, things like salad dressing, okay? You can see the little different pieces in there. Okay? We're going to talk a little bit more in depth about different types of heterogeneous mixtures. And then we'll move on to homogeneous. Anyway. First one is a suspension. Okay. As it says, a suspension is a mixture containing particles that settle out if left undisturbed. Okay. Basically what it's saying is you have particles that are suspended in the mixture. Okay. And if you just let it sit, the particles will slowly fall to the bottom. Okay. Slowly just fall. And you can see that in the picture on page 476. You have that one beaker, which obviously has a bunch of dirt stirred up into it. But if you let it sit long enough, all of that dirt's going to settle to the bottom. Okay. Sometimes liquid medicines are sold as suspensions, which is why you have to shake them first, because all of the medicine that you're interested in settles out to the bottom. But you want to actually get medicine instead of just the flavored water that comes with it. So you have to shake it. Okay. So if it's a suspension, it'll settle out, so you have to shake it to mix it up again. Okay. The next one, thixotropic mixtures. Okay. Basically, a substance that is solid, acts like a solid when it's at rest, but can flow like a liquid if you put pressure on it. That's thixotropic. So think toothpaste. Okay. Toothpaste, if you just let it sit, it looks pretty solid. Okay. It retains its shape and everything. But when you apply pressure to the tube, it flows out like a liquid. Okay. That's what we're talking about with thixotropic mixtures. There are some soils, some ground that are thixotropic, and that's a problem, like for earthquakes, because they act solid until you start applying pressure to them, and then they act like a liquid. And you can imagine what's going to happen to your house if it's built on something that's acting like a liquid. So builders in earthquake zones have to take that into account. Okay. And then we get colloids. Okay. Now, colloids are a lot like suspensions. The biggest difference is the pieces are much, much smaller. Okay. And because the mixtures are, or the pieces are so much smaller, they don't settle out. So a colloid, the pieces, you don't have to shake it up to remix it. Okay. For example, the milk that you have in your fridge, it's a colloid. Okay. We have different things, but they are spread evenly throughout. Okay. It doesn't separate. So, as you can see, there are different types of colloids. We can have, it has what, 8 different types depending on what you're mixing. And I'm sure you'll recognize several things in there, like gemstones, your blood, butter, cheese, milk, mayonnaise, marshmallows, whipped cream, smoke, clouds, things like that. So you can look through and see, what is mixed with what to make those different things. I'm not going to put it on the test, like give me an example of this type of colloid. But yeah. So. The reason, essentially, why colloids don't settle out is because of this concept called Brownian motion. It was discovered and named after Robert Brown, so Brownian motion. Basically, they're small enough that as the particles move around, okay, we get basically collisions and interactions that keep them where they are in this mixture. Okay. With a suspension, Will you have those collisions and interactions? Yes, but the particles are too big, and so the force of gravity is stronger than the forces by Brownian motion. So. All right. The book talks about the Tyndall effect. I don't care that you know what that is. You're welcome to read it. Basically, it's why some things look the way they do. So, yeah, we're just going to skip it. Now let's talk about homogeneous mixtures. That is a mixture where you can't tell the different pieces apart. Okay? Another name for a homogeneous mixture is a solution. So we are going to be working with solutions quite a bit. In fact, anytime we're working with something that is aqueous, okay, dissolved in water, that's a solution. Okay, so we'll see plenty of them as we go through class. Once again, we have different types, or we can have lots of different solutions, and they can be in the different phases. We can have a gas solution. The air all around you is a solution. You have a mixture of nitrogen and oxygen and a few other things. Okay. But it's mixed evenly, and you can't say, oh, well, here's some oxygen right here, and there's nitrogen over here, and the oxygen doesn't settle out. It's a solution. Okay. Liquid solutions are probably the most common because you can do so many things. I mean, you dissolve anything in water, you've got a solution. Okay. If you're in the kitchen cooking and you put salt in water, you have made a solution. Okay. If I'm trying to think of an example that you might think is interesting. Any of you drink soda?
No.
All things in moderation. So, I mean, yeah, you shouldn't just exclusively drink soda as the only thing you ever drink.
Yeah, no one drinks soda.
No, I didn't like that's healthy right there.
But anyway, that's a solution. Okay. That actually has a couple different things going on. We have that syrup, which is mixed with water, which forms a solution. Okay. I don't know if any of you know how those soda machines work. Like actually, like if you go to the, so it's not powder. It's actually it's a liquid syrup. It's really really thick, and so they have basically it comes in a bag inside a box, and so you hook that up to the soda machine, and it pulls the right amount of syrup and mixes it with water and all of that. So, but yeah, that's why you can have soda machines that they don't keep the full soda in there. It's just a syrup. So it mixes it, but it also mixes it with carbon dioxide gas. So we dissolve carbon dioxide in there. Now, if you have like a can or a bottle, it's going to be a little bit different than from the soda fountain. But anyway, solutions. Solutions are all over the place. You'll see them everywhere. So, that being said, not everything forms solutions. So if you have a container, you put some oil in there and you put some water in there, what's going to happen? It's separate. Okay. Now you can mix them up, but they're probably going to separate again. If you mix them enough, you can force them to stay together. You have to form what's called an emulsion, and it takes quite a bit of mixing. That's how we make butter. So. But anyway, if they readily will mix together, if they, you put them together and they just mix, we have some terms for that. Okay. If you have two liquids, okay, that mix together well to form a solution, we call those miscible. Okay, miscible, miscible. If you have a solid that's going into a liquid, we call that soluble. Okay. If something is water soluble, that means it dissolves in water. Likewise, go in the other direction. Like if you put a rock in water, it's not going to dissolve. So we call that insoluble. And the oil and water are immiscible. So just some terms that you need to be aware of. So that was section 1. Section 1 is basically, here's some terms and vocabulary and stuff like that. We're more interested in section 2 because that's where the math is. Yay! Okay. Now, the thing about solutions you can have the same two materials mixed together, but that doesn't mean that they're always the same. So for example, let's say we have 2 cups sitting on this table right here. And I tell you, I've dissolved a little bit of salt in both of these cups. Now, one of them has 1 gram of salt in it, and the other one has 50 grams of salt in it. Which one would you rather drink? The 1 gram. 50 grams in a cup, that's a significant amount of salt. Okay. So the difference is, and we would say, they have a different concentration. Okay. The one with 50 grams would have a higher concentration. So there are a lot of different ways that we can calculate concentration. And we have a table of them on page 480. So we've got percent by mass, percent by volume, molarity, molality, and mole fraction. And they're all useful in their own unique circumstance. The one that we use the most is molarity. But we'll talk about these other ones as well. Okay. Now, percent by mass. That's pretty straightforward. You guys know how to do percentages, right? Okay. Like if you got 58 out of 60 on a test, you would know how to find what percent you got. Okay. You just take the 58, divide it by 60, and you're good. We're doing something very similar with percent by mass. And it gives you Good thing you're not in 8th grade. So, for many reasons, because who would want to go back to 8th grade?
We have no homework.
Okay. So, percent by mass. It gives us our formula here. So the percent by mass, the mass of the solute, which is what you're dissolving, divided by the mass of the solution, multiplied by 100 because it's percent. Okay, so we need to make sure we understand, okay, it's the mass of the solution. Okay, so it's the whole thing. So let's look at this example problem. So in order to maintain a sodium chloride concentration similar to ocean water, an aquarium must contain 3.6 grams sodium chloride per 100 grams of water. What is the percent by mass? Okay. Now you might be tempted to just say, well, it's 3.6. You take 3.6 grams divided by 100, it's 3.6%. But you need to look a little closer. Okay. Because yes, the mass of the solute is 3.6 grams. But the mass of the solution is that. Okay. That's the trickiest thing about this, is that you need to understand you have to add your solvent with your solute. Okay? So the solvent is what you're dissolving in, the solute is what you're dissolving. So, but beyond that, it's actually really, really simple. Pull out your calculator, you do 3.6 divided by 103.6 multiplied by 100, and the mass percent is 3.5%. Does that make sense? Pretty straightforward. It's just percentages. Okay. Percent by volume, almost identical. What are we going to change when we're dealing with percent by volume instead of percent by mass? What's going to be different? What's going to be different between percent by volume and percent by mass? You're overthinking it.
One is mass, one is volume.
There we go. Instead of using mass, we're going to use volume. Okay. Volume of solute and volume of solution. Now this one doesn't have an example problem to go with it, simply because it is so similar to percent by mass, but we can go through one of these practice problems that it has. You don't want to? You want me to just sit down and give you the homework?
Yeah.
I mean, because that makes my job a whole lot easier if I just say this is the homework assignment, read the book and figure it out. I mean, anyway, so this practice problem here, what is the percent by volume of ethanol in a solution that contains 35 milliliters of ethanol dissolved in 155 milliliters of water? Okay. So the volume of our solute is the ethanol, 35 milliliters. And we dissolve that in 155 milliliters of water. But we have to add in that extra 35 milliliters because now that's the total in the solution. Just go to our calculator. 35 divided by 155 plus 35 multiplied by 100 gives us 18%. Right. So, percent by mass, percent by volume, pretty straightforward. Okay. Take whatever you're dissolving, divide it by the total of what you have after it's been mixed together. So, okay. Now let's talk about molarity. This is, like I said, the one that we're going to use the most. This is going to be the one that's most common to see. And molarity, which we do represent with a capital M, it's simply moles of solute divided by liters of solution. Moles of solute divided by liters of solution. Okay. So let's look at this example problem and just go through it. So a 100.5 milliliter intravenous solution contains 5.10 grams of glucose. What is the molarity of this solution? The molar mass of glucose is 180.16 grams per mole. Okay. So we need the molarity. Okay. Moles of solute divided by liters of solution. You can watch the rest on YouTube. So. Anyway, so it tells us that we have 100.5 milliliters. Can we throw that into our equation right like that?
No. No. You gotta put it in more. Wait.
Is that going to be moles?
What does ML stand for?
Milliliters.
Yeah, we need it.
Thank you, Mr. White.
So we do need to change it, but we're not going to change it to moles.
Oh, 2 liters?
We're going to change it to liters.
Oh my gosh.
How do we change milliliters to liters?
Divided by 1,000.
Okay.
1,000.
The poster on the board.
Oh.
Oh, so move it over 3.
Yeah, so we just move the decimal right there. So we have that many liters. Okay. It also tells us that we have 5.10 grams of glucose. Can we put that into our equation like that? Can we just put
No.
5.1 right there?
No.
Why not?
It's unacceptable.
Because this is a mass with grams, and we need
Liters. Moles.
moles. Okay? But that's something that at this point, hopefully you can do. grams to moles. Okay? Especially because the problem gives us the molar mass. Okay? So we take 5.10 grams. We know that in 1 mole, according to our problem, 180.16. Okay. So we do that, and that's going to tell us how many moles we have. Okay. Happens to be 0.0283. So that now can go right there. Now, do we have any units that we can cancel out? No, there's no units that cancel out. So our final unit is going to be moles per liter, which equals molarity. Okay, molarity is measured in moles per liter. Okay. So now we just go to our calculator, throw that in, and it gives us 0.282 molar. That's how we say it. So it's kind of like the bigger teeth that you have in the back of your mouth, molars. Okay, if you know that. But yeah, so 0.282 molar is how we would say that. It is a 0.282 molar solution of glucose. Okay. It goes through how you would create one of these molar solutions in the lab. The fact is, I do all of that work for you just to save time. But essentially, what you're going to do, you're going to mass out how many moles you need. Okay? You'd be doing this conversion, but in the opposite direction. So if you needed a 3 molar solution, how many grams is 3 moles of whatever you're dissolving? You put it in a little bit of water to make it dissolve, and then you would fill up the water to the final volume. But like I said, I do that for you because it's time consuming and yeah. But like I said, I mean, the hardest part of doing it is calculating this right here, which hopefully you're comfortable with at this point. Say, how many moles do I need? Okay. Now, how many moles you need is affected by how many liters you're going to make. Okay. Because you don't want to waste the ton. If you only need half a liter, well, only make half a liter. But that means you need half as many moles. Okay. A lot of times, what happens in chemistry is you'll either make or you will buy a solution that is more concentrated than you need. It costs less to ship smaller things. So it's usually it's a cheaper way to get your chemicals, to buy them in a higher concentration and then add the water yourself. It's typically what I will do. I have some concentrated stock solutions, and then you dilute them. Okay. But of course, as with everything, you need to know how much water to add. And we have an equation for that. But it's super easy. Just that. Okay. The M is the molarity, and the V is the volume. Okay. Now, once again, the 1s and 2s really don't matter as long as you keep everything together where it's supposed to be. Okay. That's the hardest part about this, is making sure everything comes together the way it's supposed to. So let's look at this example problem. So if you know the concentration and volume of the stock solution you want to prepare, you can calculate the volume of stock solution you will need. So what volume in milliliters of 2.00 molar calcium chloride would you need, or would you use to make 0.5 liters of 0.300 molar? Okay. So let's write out our variables. So as we go through the problem, what volume in milliliters of 2.00 molar? Okay. Anytime you see that M, that big M, you're dealing with concentration. So let's just put it right here. M1. Okay. We could have put it there as long as we keep everything together, but it's the first one we ran into, so let's put it on 1. And you want to make 0.5 liters of 0.3 molar. So the next thing that we found is 0.5 liters. Does it go in V1 or V2?
V2.
V2? Why?
Because that's what you're wanting to end up with.
Okay, good. And then our other concentration. Look at that. We have all but one. Okay, that's going to be the theme of this class. You get all but one. Tell me the last one. Okay. So we solve for V1 by itself. Okay. And now we just have to throw everything in. Okay. So that's 3. Okay. So the molarities cancel out. We're left with a volume measurement. So this gives us, if you put that into our calculator, that. But wait, there's more. There's always more. What unit did the problem ask for? Milliliters. Milliliters. So milli is 10 to the minus 3. So it would be
7 to the minus.
Mr. Wright,
yes,
could you send Wendy down, please?
absolutely.
Thank you. You can pay me later.
So,
Bye.
see ya. So it's pretty, it's pretty straightforward. You're going to get 3 out of the 4. Like I said, the hardest part is making sure you don't put this volume right there.
Yeah.
And then we have molality. Now, molality is similar. So for molarity, we had moles of solute divided by liters of solution. For molality, we have moles solute divided by kilograms. Okay. Kilograms of solvent. Okay. So this is the first time where we haven't been dealing with solution in the denominator. This one is, it only matters about the solvent. Now, molality is not that common because volume is a lot more common to measure when you're doing this rather than kilograms. Molality is mostly for things where very, very small differences can throw off your work. Because temperature affects the volume of stuff. Okay. Now, the fact is, the volume difference with water at different temperatures is almost nothing. Okay. So for most things, molarity is just fine. But if you need to be absolutely precise, you can use molality, because it doesn't matter what temperature it is, it's always going to have the same mass. Okay. So once again, we have an example. In the lab, student adds 4.5 grams of sodium chloride to 100 grams of water. Calculate the molality. This. So we have 4.5 grams sodium chloride and 100 grams of water. Okay. First off, which one is the solvent? What are we dissolving in? Which one of these two things are we going to be dissolving in? So we're putting it into the water. Okay. So water is the solvent. Can we put this straight into our equation? No, why not? Because it's in grams. What do we need it in? We need it in kilograms. Okay. Which, once again, if you're not familiar with, there's our chart over there. Kilo is basically the opposite of milli. So 100 grams is actually 0.100 kilogram. So now that we can put straight into our problem here. So this is molality, which is little m. So, okay. So we got rid of that. What are we going to do with that? Change it to moles. Very good.
Quick interruption. Can I get middle school girls basketball team down to the lobby, please? I need the middle school
Everybody at
girls
this point.
basketball
My
team down to
goodness.
the lobby. Thank you.
Half the school has been called down this period. Okay. That is a conversion. So we need to know how many grams are in 1 mole. Go to the periodic table, we take sodium, we take chlorine, we add them together, we get 58.44.
Wait, what did we add?
Sodium and chlorine. One of each, because we need the molar mass of sodium chloride.
Okay.
So we get that. We do that math, and that tells us of 0.77 moles. Then we can put into our problem. Okay. And that tells us that it is a 0.77 molal solution. Okay. Now the last one is mole fraction. We're going to skip it.
Yay.
Okay. Never in all of my years doing actual chemistry did I ever use mole fraction. So I've just made the decision that as I teach it, I'm going to skip it. One less thing for you to remember. So it's not that you can't do it. It's just we've already given you 4 other ways to calculate concentration today. And if we're never going to use the 5th one, let's not worry about it. So, questions about that? Okay. Well then, I'll let you start on some homework. So we are in chapter 14 now, and we'll do these numbers.